Talking. So we were discussing the power system stability. So we have discussed that the power system stability is of the different types. So first is the voltage stability. Because the voltage level we have the interconnected system and our load also have the requirement of some voltage level. So we have to maintain that voltage level. So we have the voltage stability. So we can allow the variation of 5% in case of the voltage level. If it is more, then it will be harmful for the system and system may lose its stability. System may collapse if there is a voltage level more than 5%. Then we have the other common parameter in the power system is the frequency, which the frequency of the system must be maintained at the 50 hertz. So we allow only the variation of 1% in the frequency, means from 49.5 hertz to 50.5 hertz. Then our rotor is rotating. Due to the rotation of the rotor, the power is produced. So means when the rotor is rotating, it moves and it has some angular motion. So due to this, the rotor has some angular stability also, because when there is a change in the load or some disturbance occurs in the system, your rotor angle changes, and this rotor angle is known as the load angle. So this delta we call here as a load angle. So means when the rotor changes, when the rotor means under the steady state conditions, when you put some load on the rotor, so we have some angle delta of the rotor with respect to the revolving synchronous speed. We have the revolving synchronous axis. With respect to that axis, your rotor has some angle delta. And due to that angle delta, your synchronous machine is producing some power or it is consuming some power. If your delta becomes 0, then the value of your real power which is produced or which is means consumed in case of motor will be 0. So we need some value of delta for this purpose. So when there is a disturbance, so this delta tries to change. So when let us suppose we have increased the load or we have given the more mechanical power to a generator. So in case of motor, if we increase the load, then your motor will slows down. When the motor slows down, in case of the motor, your rotor axis is lagging behind the synchronously revolving field. So when the motor slows down, more slows down, then delta will increase more. And in case of the generator, your rotor axis is leading the synchronously rotating field. So when we give the more mechanical power, so your rotor will more advance as compared to the synchronous speed. So there will be the change in the rotor position. Similarly, your change can be plus or it can be minus. So when there is a change in the value of the delta, so your machine tries to adjust at the new position, because when your machine is under the steady state condition, so at a particular value of, let us suppose during the starting case, your value of delta is delta 0, initial steady state condition delta 0. So when your machine is running at delta 0, under that case your synchronously revolving field has a synchronous speed. Similarly, rotor also rotates at a synchronous speed. Both the synchronously rotating field and the rotor have the synchronous moving synchronously, and rotor locked at that position, means the rotor is locked in the field at that position. When there is a disturbance, so your delta changes and your rotor tries to adjust a new position. So in this adjustment, if there is more disturbance, so your rotor may go out of the synchronism and your machine may become unstable, or Machine will be stable if ultimately after the disturbance rotor settles down at a new position or at the old position and again starts running at the synchronous speed. So under that case we are saying that machine is a your stable. Machine will be stable, running in the stable condition. So we have the angular stability. We have the different types of the angular stability. So first, angular stability is a steady state stability. Means when we gradually increase the load. If we gradually increase the load, we are slowly increasing the load. So when we slowly increase the load means your rotor is not losing the synchronism. Rotor is not losing the synchronism, but its angle delta is gradually changing. So there is a limit for the gradual increase in the load or gradual disturbance that your delta should not become more than or equal to 90 degrees. Means your delta must be less than 90 degree in case of the steady state conditions. So other is the transient stability. In case of the transient stability, this is a means of more disturbance, sharp disturbance. So this type of disturbance is due to the your faults in the system. This is short circuit occurs in the system. So immediately your system will be disturbed. So means we have the when the short circuit occurs. So we have the either the your fault is cleared automatically after some time, or it is cleared with the help of breakers. We have the breakers in the power system, and those breakers clear the fault after some time. Your breaker clears the fault and rotor tries to adjust at the position, at the synchronous position. And if it adjusts, if means the disturbance delta starts, change in delta starts reducing, then we can say our system will be stable. Otherwise, we can say our system will be unstable. So we can say that we have the disturbance in the delta, your delta is disturbed with respect to time. So initially, this is the time. So initially, let us suppose your delta is at delta 0. Your value of delta is at delta 0. So due to this disturbance, your time starts from this instant. When the disturbance occurs, your time starts. So here your time is 0. So it means your delta will increase or decrease. So means your increase or decrease in delta will start. If this delta continuously increasing, if delta is continuously increasing, then we can say our system is unstable. It will not come back to the original position, and this delta will be out of control and your machine will lose the synchronism. So other state is, so this state is known as a unstable system. This is the state of the unstable system. Now if his position is like this, that after some time, let us suppose means you have a disturbance, but after the increase, there is a means the rate of change of this delta is reducing, and here the rate of change becomes 0, and after that this delta becomes negative, then again positive, then negative, positive, negative. Ultimately, it settles down to a new delta value. So we can say that after the disturbance, if your delta settles down, means delta starts reducing or the rate of change of delta after the any disturbance becomes 0, we can say our system is a stable system. Otherwise, if your delta is continuously increasing, then we can say our system is a unstable system. So we have the different types of the stability. First is the steady state stability, steady state stability, then transient stability, dynamic stability, like this. So also in the previous class, we have observed that the power which is transferred by the machine, electrical power, is given by PE is equal to E V X by sine delta. ठीक है? Means if it is the initial conditions, under the initial condition, we have the P delta curve is like this, delta, and on this side is your P. So under the initial case, let us suppose here your PE was PE0 and delta was delta 0. So it is the initial steady state condition. Before the disturbance, it was the initial steady state condition. So under that case, our this PE0 is equal to sine delta 0. So E, what is E? E is the voltage level at the generator bus. So let us suppose this voltage level is equal to E into delta. And this generator is supplying to a unfinite bus. Unfinite bus means its voltage level is not changing. How much power we give it to, or how much power we can take it from this, and its level is not changing. That is why this is known as a unfinite bus. So let us suppose the voltage level of this bus is infinite bus is V0. Means the voltage phasor is lying across the reference axis, and the power which is flowing through the line is having the reactance X. So then the power which is flowing, electrical power PE, will be equal to, is given by this equation, EVX by sine delta. E is the voltage level here, V is the voltage level here, X is the your reactance of the, or we can say the impedance, or out of the impedance we have neglected the resistance. So our line, our conductor mostly have the reactance. That is why we have taken the reactance here. And sine delta means the initial angle difference. Initial angle difference between the your voltage and the E, that is delta 0. So means we, in this case, in the voltage curve, this is the electrical power. This is the electrical power curve. Means the electrical variation of the electrical power with respect to delta. Also, we are giving the mechanical power, or we are taking the mechanical power from the machine. So let us suppose that mechanical power is given by like this, PM, mechanical power. Or we can say that this mechanical power is equal to the shaft power, the power which is supplied at the shaft of the machine. So we can say this is equal to PSH, shaft power. So under initial steady state conditions, under initial we have the your your PM minus PE in case of generator, which is known as the accelerating power. This is known as the accelerating power. So this accelerating power means when your machine is under a steady state condition, so your delta is not changing. So under that case, if your machine is a lossless machine, means that there is no fractional or windage losses in the machine. How much power we are supplying, that will be equal to the power we are getting from the machine. So your, under that case, your this PM and your this PM will be equal to PE, or we can say the acceleration between PM and PE is equal to 0. So under that case, your this PA is equal to 0, or your PE is equal to PM. Okay? So from in this case, means if you have some values are given with under steady state condition, some problem is given to you, that this is the shaft power under the steady state condition, or this is the electrical power